Is that frozen?
So we wait. And oh my gosh.
We good?
Seems like we're good.
Alright, cool. Cool. Alright, hello everyone. Welcome to the TELE3113 crash course. Thank you for anyone online watching. First of all, the attendance form for the crash course is here. Please fill it out, and the link to all the crash course slides are on there. Yep, as you can see on the projector, that is the QR code. My name is Jackson, and I'll be running through the first kind of half of this crash course, and then my mate Otto, exec, will be running through the later half of the crash course. Cool. So let's get into it. Cool. So just going through some of the crash course contents. The first three topics will be analog, amplitude modulation, angle, and then interference and noise. And then we'll be moving on to how you actually move from your analog to your digital domain. And then we'll be looking at purely digital telecommunications. Some exam tips from Mohammed. As it is important to look at past paper questions, he also emphasized that it's really important to understand the concepts. A lot of the questions will be purely conceptual, and there'll be a lot of questions asking for like explanation of block diagrams, specifically in terms of modulation and demodulation. Cool. And also feel free to use these slides. I spent a lot of time making them. I think they are very good for revision. I'm sorry if I've missed anything. Alright, jumping into topic 1, amplitude modulation. So your amplitude modulation is a nice introduction into modulation. So we have this modulated signal S of t, which is given by the amplitude of your carrier, 1 plus Ka, which is your amplitude sensitivity factor, multiplied by a message, and then by your cosine of omega ct. Cool. Just a couple of things to note with this form. I've highlighted in red the envelope, and what I mean by the envelope is this waveform here that we have sitting above the modulated wave. That is going to be some proportion of our message mt. This here is our carrier, and this is our amplitude. Yep. Then moving on to our modulation index, mu. Mu is given by am times Ka. Some things to note with mu. The value of mu is very important, specifically when your mu value starts to approach 1. When you approach 1, the envelope hits exactly on the time axis, and anything beyond that, the actual signal the envelope will intersect the time axis and come through like this. And this is a major issue because then we get what are called zero crossings. And we'll get into why that is important later on. Some other things to note, when you're ever asked to find the amplitude of a sinusoid, the formula is given by AC squared on 2. And if you ever need to find the efficiency of a AM wave, you would find that using this formula here. So just noting that mu for AM signals has to be less than 1, otherwise we get these zero crossings, which means that we are limited to an efficiency of 33%, which is not that great. Looking at the frequency spectrum, in the frequency spectrum we have 2 bands which correspond to our carriers, which are denoted by these arrows here, and then we have the frequency shifted message, which is given by these triangles here. Cool, moving on. So there's 2 ways to demodulate an AM signal. The first one being the simpler one, envelope detection. The way envelope detection works is first we pass through our signal through a rectifier diode. So by rectifier, what that means is we're basically removing all of the negative components of our carrier, And we do this so that our low pass filter later on can can better follow this shape of the wave. And this red waveform is what we get at the output. Cool. The issue with this when we have zero crossings is when you have some sort of waveform that crosses through the axis. What the envelope detector will try to do is it'll try to follow the positive part, and we'll get some sort of distortion like this, which very obviously is not a sinusoid. Moving on to coherent detection. Coherent detection is applicable to a wider range of modulation schemes, and it does deal with the fact that you may have these zero crossings. Just to prove that it works even with zero crossings, I'll do a quick derivation. So looking at this first part, we're multiplying our S of t with our carrier. So we'll get y of t is our carrier. Multiplied by our S of t. Noting that our S of t is given by this formula, we will get some sort of output that might look like this. So then to simplify this, I'm just going to use this identity where the square of a cos is given by half of 1 plus cos of 2 omega c t. And that will give us a form that looks something like this. AC on 2, 1 plus cos 2 omega c t plus AC Ka on 2 m of t and then 1 plus cos omega 2 omega c t. So what happens with this is after we've multiplied through, this low pass filter is going to try and remove any high frequency components. So in terms of high frequency, we have this 2 omega c term here, and we have this 2 omega c term here. So those will be removed by the low pass filter. And then we're left with an AC on 2 term and an AC Ka on 2 times MT term. What might happen after this is we might AC couple this output, and we'll get some final output, YD of t, which is simply just this component here, which is AC Ka on 2 MT. So we find that in this case it doesn't actually matter what Ka is, so we can have zero crossings occur and it will still be able to detect. One drawback with this detection is that we need to make sure that the phases of our carrier that we're multiplying by and our modulated signal, they have the same phase. When we don't have the same phase, so if the carrier phase does not equal the S of t phase, then we will have some sort of output that is proportional to the message multiplied by a cos phi of c minus phi of s term. And the issue with this is, for example, if this phase difference is 90, then we know that cos of 90 would give you an amplitude of 0. So then in that case, we don't actually have an output. Yeah, question?
The previous part, would you also have an AC on 2 added? Because it's AC on 2 times 1 plus 0.
Oh, this one here?
Yeah.
We would, but often what happens is we do some sort of AC coupling. So for example, maybe sticking on a capacitor to remove any DC component. So that in that way, we get rid of that DC term, and we're just left with the AC Ka on 2. Cool, makes sense. Sweet. Cool, so that's coherent detection. It'll come up a lot in later sections, so make sure you put this to memory. It's very important. Moving on to generation of AM waves. So to modulate an AM wave, we just have this block diagram here, which is simply a model of this form. You can do the working out yourself, but you'll find that you'll get the same SFT. On to other forms of amplitude modulation. First of all, we have double sideband single carrier, which is denoted here. One important thing to note with double sideband is that we no longer have these carrier bands coming out at omega c and negative omega c. And the benefit of that is that we're not wasting energy on transmitting a carrier. As we saw for AM, we get a maximum efficiency of 33%, but because we don't have that carrier to transmit, we can actually transmit with an efficiency of up to 100%, which is amazing. Bandwidth will remain the same. This changes when we go to single sideband. So single sideband, there's two different forms of single sideband. The one you see here on the diagram, this is upper single sideband. Lower single sideband would look something like this. So looking at this formula, lower single sideband is when you have this negative here, upper single sideband would be when you have this positive term here. Cool. So the benefit of single sideband is that you can transmit the message with an even lower bandwidth of omega, which is half of DSB and for AM, and you still get that efficiency of 100%. The only issue with transmitting an SSB modulated wave would be you need to create this really sharp cutoff, which can be quite hard to produce in practice. So as sort of a middle ground, we also have this vestigial sideband single carrier, which is an in-between of DSB and SSB, where we have this most of one of the halves, and then we have some smaller amount of the other sideband. So this might be done using some sort of bandpass filter, similarly to SSB, but we're allowing a larger transition band in that filter. Cool. So then just noting the ranges for bandwidth and efficiency will be in between that of AM and SSB. Lastly, we have QAM. QAM is amazing because we can transmit 2 messages for the price of 1. As we can see in the frequency domain, we have 2 messages that can be transmitted at the same carrier frequency because they are orthogonal to each other, which we can see denoted by this cos term and this sine term. Onto the block diagrams. DSB is simply 2 AM modulators multiplied by the same carrier frequency, and then you subtract one from the other to get DSB. SSB is quite similar, but in this case you are phase shifting one of your products so that when you subtract you will end up removing one of the sidebands. With QAM, QAM is essentially 2 DSB modulations, but one of them is with respect to a sine because of this 90-degree phase shift. And when you're demodulating QAM, you will find that you essentially have 2 coherent detectors. So these are each coherent. And these will be 90 degrees out of phase because our 2 messages are 90 degrees out of phase. Lastly, we have VSB modulation. This should be DSB, not DBS. So as we talked about earlier, you would modulate to get a DSB signal, and then you would then pass it through a bandpass filter to cut off some of one of those sidebands. Cool. So we'll jump into a question. Question 1. A message MT is passed as an input to an upper single sideband suppressed carrier modulation system with a sinusoidal carrier frequency having a frequency of 10 kHz and amplitude of AC. To save us a bit of time, I have written out the solution for this question. So to find an upper single sideband, I think the easiest way to go about this would be first to find our DSB signal and then just to remove the half that we're not interested in this case the lowest sideband. So to do this, if we recall, DSB is found by simply multiplying your message with your carrier. Expanding this out, we get this expression here. And then using this identity, cos A, cos B, we will get a simplified expression for our DSB. And we can see here that we end up with 4 terms with 4 different frequencies. And these denotes the upper and lower sidebands of each message. So to remove the lower sidebands, I'm just going to simply assume these get cut out and ignore them, so that we are left with this form here. And lastly, to convert to the frequency domain, I'm going to use this identity here to get this final expression. So we'll see that when we plot the spectrum at f of c, we won't have a carrier because it's SSB, and we will have the upper sidebands of the 2 messages we are transmitting. When we are plotting the phase, as we can tell from this expression for the frequency, there's no complex term, so we won't actually have a phase attached to these terms, so there won't actually be any phase at all. So these will just be 0 at each of these bands. Next, to find bandwidth. The bandwidth of the transmitted message is sometimes different to the bandwidth of the message itself, but in this case for SSB, they are the same. So to find the transmission bandwidth, we would just look at this range of frequencies here, which turns out to be 200. And then when we look at our message, we will have the exact same, 200. If we had something like DSB might look something like, if this is your carrier, you would have bands either side, and that means that your total transmission bandwidth would be twice of your message bandwidth, which would be 400 Hertz. Lastly, we were asked to find the power in terms of AC. If we remember from the first slide in this crash course, the power of a sinusoid is given by a squared on 2. So considering these to be our A's, we just have to square them and divide them by 2, as we can see here, which gives us a final expression of 5 AC squared on 4. Does anyone have any questions about that? All good, okay. Moving on to the second topic, angle modulation. There's 2 main forms of angle modulation, frequency and phase. The relationship between these 2 can be seen when we look at the phase attached to each of these cosine terms, or each of these carriers. We see that this M of t has an integration attached to it, whereas in phase modulation we don't. So to see the relation between the 2, they're essentially related by an integral and a derivative. Some other important things to note: the modulation index, denoted by these formulae. And lastly, we have these formulas here, which is simply showing that the power of the AM wave that we've discussed has a power that depends on the message frequency itself and its amplitude at a specific time, whereas for frequency and pulse modulation, phase modulation, we have a constant amplitude, a constant maximum amplitude. So this is sometimes preferred in transmission because we're not varying power with time as much, which can be a desired property. Looking at the difference between these graphically, so frequency modulation, it changes frequency with respect to the amplitude of your message. So we can see that when you have your lowest amplitude in your message, you have the lowest frequency, which is quite a large period. When you have your highest amplitude, you will have your highest frequency. As for phase, if we recall, phase is related by this derivative term. So we would find that it's changing the fastest. It has a fastest frequency when you have the fastest rate of change in the positive direction. And when you have your most negative rate of change, you would have the lowest frequency, which is quite a large period. Looking deeper into FM, there are two main forms of FM, narrowband FM and wideband FM. We have two different forms because of the way that our modulation index works. When we have a beta value that is significantly less than 1, as we can tell from this table, when you have a very low beta value, you will only really get a single carrier band, and then you will have a band either side, denoted by this n equals 1 term. Whereas when you have significantly larger beta values, you might have a wider band of frequencies, which gives the name wideband. If you're ever asked to graph one of these in the frequency domain, this is the formula that we use. Simply AC on 2 times this J and beta, which is our Bessel function. And we can find the value of the Bessel function for each value of n simply looking at this table. So for example, if we have a beta value 0.1, we know that we would have 2 peaks either side of our carrier, and our carrier would have this amplitude. And then, so that is the amplitude 0.998, and then we would multiply that by AC on 2. Lastly, Carson's rule. Carson's rule is a great approximation for finding the transmission bandwidth of a wideband frequency modulated wave. There's 3 different forms. They all mean the same thing, but depending on what you're given in the question, you might want to use one over the other. All right.
What's the physical significance of beta in modulation? What is it?
Well, when you have a larger beta, you can see that you have a larger allowable range of frequencies in your modulated wave. So I would say that is the significance. Narrowband is saying that you're not allowing many different frequencies in your modulated wave, whereas wideband, when you have a larger beta, is allowing a wider bandwidth, I would say.
Is it like a filter?
Is it like a filter?
Right? That's what we're getting beta from, right?
Yeah.
To consider it like that, I think the idea is that we can only get these delta functions at certain intervals. And so by having a more comparable sinusoid attached in your phase, it allows greater distincts, I guess, amplitude levels. It's more of a, there's a funky little E equation, the Basel thing, which you might see if you look further into it, but what was the question?
Is it like a filter? I'm not sure if, I don't think you can really think of it like a filter. It's more of a property of the wave. Yeah.
It's like a wave in a wave.
Yeah. It's a bit.
It's like a start, it's just one peak, and then it broadens out, and it starts rippling outwards, which is why you get like mega values and everything.
Yeah.
But
Yeah.
it's just a funky property.
Yeah, that's
really.
right.
It's a good question.
Okay. All right, moving on to some block diagrams. This is our narrowband FM modulator. Here we have, this is the narrowband phase modulator, and to make that into a frequency modulator, we just stick this integrator at the front, just because we recall that for frequency, in your phase, you're going to have this integral term for your message. This is your wideband. So your wideband makes use of your narrowband frequency modulator and sticks on this frequency multiplier. And what this multiplier is doing is, in simplest terms, it is increasing your beta value by some factor. And as we can see from this table, when you increase your beta value, you're increasing the bandwidth and the number of peaks you allow to transmit. Indirect FM is not particularly important. I might just go straight onto this frequency discriminator. So frequency discriminator has two paths. This first upper path is determining the positive rates of change in your circuit. So positive ds of t on dt, whereas this negative one is tracking your negative rates of change. And that's simply a consequence of the physical circuits that we can create. We have to sort of split it up in that way. And the reason that this discriminator works is if we look at s of t and its derivative, s of t might be given by something like ac cos 2 pi fct plus, and then you would have your 2 pi kf, that should be small f, and then your integral of your message. When you track the derivative of this, you will get a term out the front that is directly the derivative of what's on the inside. So you would have an AC negative because we're differentiating cos, and then you would have a 2 pi FC plus 2 pi KF, and this integral simply disappears. So that is your envelope, and then you would have sine of what's up there. So what we see is we get this envelope which is directly proportional to our message. So that when we pass it through an envelope detector, what we get is something proportional to our message. So that's, in essence, how our direct FM modulation works using a frequency discriminator. Our indirect method is our phase lock loop. Phase lock loops are pretty incredible. They're used widely in telecommunications, control systems, what else? Electronics, I guess. A lot of fields of electrical engineering. The way it works is looking at the output of this voltage controlled oscillator. When we take the product with the incoming wave, this E of t will give us some phase that is proportional to the difference in phases of our incoming signal and our R of t. And what this loop filter will try to do is it will try to minimize this difference in phase between S of t and R of t, eventually taking it to something very, very close to zero, which is what we call a phase lock. And when that happens, we have a difference in our phases of zero, which inevitably means that our derivative will also have a difference of zero, as we can see here, which means the derivative of your input phase is equal to the derivative of your output phase. If we recall, frequency is related to phase by the derivative, so that would mean that our frequencies have to be equal at the input and the output. And then we have this linearized PLL model, which is simply a more specific model of the phase lock loop, just looking specifically at demodulating FM waves, which is more of a realistic model of how we might demodulate in a practical environment. Are there any questions on the phase lock loop? Yeah?
So does the second diagram just talk about the whole circuit in terms of phases? Is it essentially the same as your first diagram?
I believe so. This would be your incoming signal S of t, right?
Right.
And then this would be your R of t. Is your question why these are here?
Yeah.
I'm assuming you know the answer to this, which is why you asked.
It's just a good question.
It's a good question.
It's a good question.
Oh wait, you're right. Because this sum is directly saying that you are taking the difference of these phases, right?
Yeah.
Cool. So yeah, this is directly saying that phi e is equal to phi 1 subtracted by phi 2. And then yeah, the rest of this diagram would be dealing with this phi e term, which is directly in terms of phases, rather than over here when you're dealing in terms of the actual modulated wave itself.
Why do you times the
Yeah, if I was to go into depth on like why all these coefficients are there, I would probably have to go through the entire derivation. All of it is on the lecture slides. Basically, this is just the block diagram modeling some linearized output that you would get from linearizing a PLL model. By linearizing, it's just saying that when we look at a time variation that's minute, we can assume that the change in phase is linear, and that allows us to do some derivation to get this linearized PLL model. Yeah. Cool. We'll move on. Cool. So given a single tone message signal M of t equals sine 2000 pi t, this signal is frequency modulated onto a carrier wave with frequency f of c is 50 megahertz and a frequency deviation of kf equals 100,000. We are first asked to express the FM modulated signal in the time domain. So if we recall, for an FM signal, we would have this form, AC cos 2 pi fct plus 2 pi kf integral of m tau d tau. Subbing in our values, AC remains as AC. Our carrier frequency was 50 megahertz. KF was 100,000. And we're integrating sine of 2000 pi t. Oh, sorry, this should be a tau. Alright. I'll do this part first. So this would give you negative 1 on 2000 pi cos of 2000 pi t. Sorry, this should be a tau again, between t and 0. If we sub in t, we'll just get cos of 2000 pi t. If we sub in 0, this will be a 1. So this is equivalent to 1 on 2000 pi, 1 minus cos 2000 pi t. Subbing that back into our original formula, we will get an output AC cos 2 pi times 50 megahertz t. This 2 pi will cancel out with this pi, and this 2 will become a 1, and then we can remove 3 zeros by cancelling it out with this 1000, so we'll get plus 1000, plus 100, 1 minus cos 2000 pi t, and that will be our FM modulated wave. Alright. Part B. What is the peak frequency deviation of this FM signal, and what is the modulation index? So if we recall, this part here denotes our instantaneous phase. To find our instantaneous frequency, this will be the derivative of our instantaneous phase. So taking the derivative of this, we would get 2 pi times 50 megahertz. This constant term will disappear, and we'll be left with the derivative of this cosine term. So that will give you plus 200,000 pi sine of 2000 pi t. So our peak frequency deviation is basically, with respect to time, what is the maximum change that occurs in the frequency with respect to our center of oscillation. So we have this sine term. Sine, as we all know, oscillates between -1 and 1. So the maximum deviation we can have is by this constant term out the front. So we have omega I is 200,000 pi. So then if we want that in hertz, we would get 100,000. Next, to ask for the modulation index. We might recall the modulation index is given by the formula up here, KF AM on FM. So we'll simply have KA FM, was that right? KA AM on FM. Or we can simply do, why don't we do this one, since we calculated the deviation. So we can do this. So this is our peak frequency deviation. So we can write that as 100,000 on 1K, which will give us a beta value of 1,000, which is very large.
Is it on 1K?
Sorry?
Is it on 1K or the central frequency?
It will be on 1K because it's your FM, your frequency of your message. Yes?
Right.
Okay, cool. So yeah, I kind of skipped that bit, but yeah.
So could you, instead of using your method basically,
Yeah.
just directly calculate the deviation with KF times AM, because it's all given essentially?
Yeah, it would give you the same result.
Okay.
Yeah. We can verify that. KF is 100,000. AM is 1 in this case. And then we'd go 1 times 100,000 divided by 1K.
You can do it that way.
Yeah, it'll give you 1,000 as well. Alright, for this part C, estimate the bandwidth of the FM signal given beta equals 1. So we calculated beta is 1,000. We're going to forget that ever happened. We're going to say beta equals 1 for this case. Using Carson's rule that we have above. We're given beta, so I'm going to use one of these formulas involving beta. I might just use this one. So we have 2 FM 1 plus beta. We know our FM is 1K. And we know our beta is 1, so 1 plus 1 is 2. So we have a bandwidth, transmission bandwidth of 4 kilohertz. Lastly, it asks us to produce a rough sketch for this FM signal. Since beta is 1, this means we will have a wideband FM signal. So I would first denote the carrier frequency we have. The carrier frequency being 15 megahertz. And then we would have sidebands corresponding to the values that we are given by the Bessel function. So looking at the Bessel function for beta equals 1, our carrier will have a magnitude of 0.765 multiplied by this AC on 2 term, and same with these other sidebands. Magnitude of 0.44, 0.15, and so on. So this will have an amplitude. Amplitude of 0.765 AC on 2. This one would have an amplitude of 0.440 AC on 2, and so on. And this would be, the frequency of this would simply be your carrier plus n times your message frequency. So this would be 50 megahertz plus 1 kilohertz, and then 50 megahertz plus 2 kilohertz, and so on. As always, we will have the same exact diagram in the negative portion of the frequency spectrum. Cool. So it would look something like that. Does anyone have any questions on this? All good. Sweet. Alright, topic 3. So topic 3 deals with 2 different ways that our transmitted signal can be distorted. The first one being interference. So interference occurs when we have some other man-made signal being transmitted somewhat closely to the carrier frequency that we've transmitted at, and that causes the received signal that we get to have some sort of interference term. I won't get into the derivation, but we can see that we get a different output depending on the relative amplitude of our carrier compared to the interference signal. When the carrier is much larger than the interference signal, we find that it doesn't have as much of an impact, and rather we just get this additional interference signal added onto our message. Whereas when our interference signal is much larger than our carrier, we will get a lot of impact. So our carrier actually changes to have a frequency of omega I, and our message frequency is multiplied by this interference signal called omega IT, which is very much an undesired effect, and it would make it very hard to then get our message out of that signal. This is where FM and PM comes in. So with FM and PM, we can see that the amplitude of your interference is inversely proportional to the amplitude of your carrier from these instantaneous phase and instantaneous frequency formulae. So we can actually quiet the impact of interference by having a larger carrier amplitude, which is something that AM cannot do. Moving on to noise, we only really deal with white noise in this course. By white noise, what's meant by that is that every frequency is equally likely to occur, so we have a flat frequency response, and in time every sample of noise will be random and uncorrelated. This is how you find the noise bandwidth of a filter, total noise at the output, and then this is your power spectral density formula here. Cool, and again, we're only looking at white noise in this course, so these formulas above only really are applying to white noise. Alright, moving into the more depth of this topic, total harmonic distortion is given by this formula here. So for example, if we have some sort of frequency response with a bunch of peaks, V1, V2, V3, V4, then these peaks simply get subbed into this formula as is. SNR is simply a ratio of how much of your signal is being received compared to how much noise is being received. The formula itself is pretty intuitive. It is the power of the signal divided by the power of your noise, hence the term ratio. And typically it is expressed in terms of decibels, which is why we have this 10 log term for power and this 20 log term for voltages. The next most important formula would be this figure of merit. Another way of writing this is your post-detection SNR over your pre-detection SNR. And what this is telling you is essentially when you modulate or demodulate, it tells you how much noise is being added or removed from the signal that you're transmitting. So we can see that for DSB, we have a figure of merit of 1, which simply means that we aren't adding or removing any sort of noise. For AM though, we have usually a figure of merit that is less than 1, which means that in most cases we'll be actually adding noise to our output, which is very undesired. And in FM, we actually have the ability to have a figure of merit that is greater than 1, which means that by doing this modulation and demodulation in FM, we're actually removing noise that is picked up when we're transmitting. Lastly, we have pre-emphasis in FM. Yep, what's up?
So, about the noise in different modulations, is there talking about is it white noise, or is there like a noise in the demodulation system itself?
It'll be, so when you transmit, you pick up some sort of noise from like external sources, and the figure of merit is essentially, if it's removing, then it's a measure of how much of that noise that we've picked up is being removed. If it's adding, that means that within our modulation system, there has been some noise added on.
So the equation that you get for AM.
Yep.
So are you saying like in DSP, for example, there's no noise added or subtracted? How do you make sure that happens?
How do you make sure that happens?
Like how is it doing that? How is it getting rid of all the noise if it's just white noise or like surrounding noise? Is it cancelling it out somehow?
Yeah, that's a good question.
Wait, what was the question?
So like in DSB, why is it actually like have a figure of merit of 1? Why is it actually removing any noise that's being added?
Or even
I believe figure of merit is more a measure of information that is obtained after transmission. Right? So DSB, you just pushed it along, which, I mean, everything gets pushed, everything gets brought back. So you essentially have the same signal just pushed around, meaning you have the same figure of merit. You see noise as it is, there's no distortion to the noise, I suppose. However, in AM and potentially FM, your noise bandwidth is going to impact different regions differently. And because there's a different effects across it, it would
and
potentially.
isn't DSP also changing your bandwidth by moving it to a different signal?
Did we run over the definitions of pre-SNR and post-SNR?
Not exactly.
That might assist with this.
Okay. Well, I think it is quite self-explanatory, but pre-SNR is like the SNR when you are sending that signal, whereas post-SNR is the SNR that you receive after you've demodulated that signal, right?
And then the reference SNR.
In most cases, we define the reference to be the pre-SNR.
Is there any difference between the reference SNR and the pre-SNR?
It's just this bandwidth here, right?
Yeah. So, I guess it helps us compare to the post-SNR then, because we're using noise of the same bandwidth.
Yeah,
So
that is the reason for that, yeah.
I suppose it's just a comparison of power in, power out, right?
It is. Power of your noise. Reference to power of your output noise.
Yeah.
Yeah.
So it's before and after, wait, is it before and after transmission or detection? Well, the
Detection.
detection.
Detection, yeah.
So I guess it's like losses in the detection also, right?
Yeah. Again, there's like the derivations for these are quite extensive. So I think there's not really a simple way to put.
I think how it's going to be understood is just that SNR AM pre over SNR AM post, for example.
Yep.
You can just divide those two and you would get KA squared P over 1 plus KA squared P.
Yeah.
Yeah.
Yeah, exactly.
In
So it's your-
DSP, yeah.
Yeah.
It's just DSP is the same for pre and post.
Yep.
Yeah.
That's why you get 1.
Yeah.
Yeah.
Like mathematically that can be understood.
Yeah, from these. But if you're asking why do these formulas exist in the first place, I think probably look back on either the textbook or the lecture slides, and it will explain that for you. Sorry, I couldn't really help with that question. Cool. All right, we'll move on to pre-emphasis. So when we transmit FM signals, what we often find is that we get amplification of noise at higher frequencies, which isn't really what we want. We want a more consistent noise at our output. So what we do is we apply a de-emphasis filter, which we can see here. So de-emphasis is really amplifying these lower frequencies and attenuating these higher frequencies, which will give us some sort of flatter output, somewhat flatter. The issue with this is when we apply the emphasis, is it also, the filter will inevitably also be applied to our signal. So our signal will also be distorted in this way using this de-emphasis filter. So what we have to do is before we transmit, we need to pre-emphasize the signal itself so that when we de-emphasize, they kind of cancel out. Which is why we see this relationship here where the pre-emphasis filter is the reciprocal of your de-emphasis filter. So your noise is directly impacted by this de-emphasis filter, whereas your transmitted signal is not. The effect of those filters are cancelled out. Alright, jumping into a question. Assume a signal MFT having the power spectral density given by this equation. Derive the expression of the post-detection SNR, i.e. SNR at the output of the receiver when we use DSB SC and then when we use AM. So first we'll look at the DSB example. When we receive a filter, when we receive a demodulated signal using DSB, we will have an output that often looks like this, which is some amplitude of your carrier multiplied by your message signal. What we're trying to find is your post-detection SNR. So to do this, you're going to need your power of your signal after the detection and the power of your noise. First, we'll look at the power of your signal. This wasn't very explicitly taught in this course, but the power of your signal can actually be found by finding the area under your frequency response. So say you have some sort of response for, say this is your SM of F, then finding the area under this curve actually tells you the total power that is being carried by that wave. So if we look at the formula for our frequency response, we have A times absolute value of F on omega. If I draw this a bit more accurately, we might have something that looks like this, something that's symmetrical about the y-axis. So taking this integration, P of S is going to be the time average of our message signal squared, which means that we will have this AC term pulled out the front being squared, and then we need to be able to find this time average or the power of the MFT itself, which we can do using this frequency response that we're given. So we have AC squared multiplied by this integral of this frequency response. What I'll do is I'll just look at this side of the frequency response and just multiply that by 2. So we have from omega to 0, and then the actual equation is F. In this case, we can remove the absolute value because we're just looking at the positive side of it on omega df. So then what we get is 2. This F will become an F squared, and we'll have a factor of 2 on the bottom. And then we sub in omega and 0. So we get AC squared times the 2's will cancel out, and we'll have A omega squared on omega, which will give us the final value AC squared A omega. So that is the power of our signal. Yep.
Why do you not consider the negative one?
It was just to simplify the calculation. So we can see from this equation that it's symmetrical about the y-axis. So I can just, if it's symmetrical, I can just look at the integral of half of it and double it, because the area of both sides will be the same.
Yeah, is that not relevant? Or are you just going to double it?
Yeah, I'm just going to double it. So I am counting it. I'm just simplifying the integral. Yeah.
One more thing. I think maybe the reason why this can be thought of as an integration is because we're going from time domain to frequency domain. So if you look at the formula for going from time domain to frequency domain, I think that involves an integral of minus infinity to infinity. So maybe you could mention, I'm not sure
like a sum of sinusoids? Like a Fourier series? Is that what you're saying?
Yeah, it's like a Fourier transform of a Fourier series, but like big enough.
Transform is not the integral.
How did you say that related to the power?
So you go from you try and find m squared t.
Yep.
And you told that it's the integral. You're saying that it's the integral of the SF.
Mm-hmm.
That's because you're going from time domain to frequency domain.
Oh, right.
To make it
I see what you mean.
spectra.
So we're just applying the Fourier transform. Okay, great.
So maybe mention
Thank you for
more,
that.
like,
Yeah. Okay, so to convert, we are just simply taking the Fourier transform, which has an integration from infinity to negative infinity f of t e to the negative j omega t dt. And that is why we can convert directly into an integral in the frequency domain. Cool. So we'll do the exact same thing to find the noise power. As we know, the noise frequency spectrum looks something like this. It's just a flat thing with an amplitude of n0. In this case, it will be bandwidth limited to the bandwidth of our detection system, which will have some bandwidth b. So we just need to take the integral of this again. So the power of the noise is given by the integral from b to negative b of n0 df, which is the same as twice the bandwidth to 0 of n0 df, which gives us 2 n0 b. So then finally, to find the post-detection SNR, we just have to take the ratio of the two. Yep.
I might be wrong about this, but isn't the noise in the frequency domain a sinc function? And in the time domain it's a stream?
If we go back up to the definition for white noise, we know that the power spectral density for your noise is a flat line.
Okay.
Yep.
If you have a pulse, it Fourier transforms into the same, and then it also inverse Fourier transforms into the same. So it's any matter transform on a pulse equals this, which is there.
Cool. So just taking the ratio of the two. In this case, we do have that beta equals omega in the case of DSB. So then we will get these two terms cancelling out, and our final SNR for post detection is AC squared A times 2 n0. Cool. In the interest of time, I will skip this second part, just because we're already an hour in, and we'll move on to topic 4. So topic 4, analog to digital. This is where it gets a bit more interesting. I've put here just a diagram of how, in general, we would go from an analog signal to a digital signal and then transmit. So after applying a low pass filter, we would sample and hold and then quantize. These two make up our pulse amplitude modulated section of this system. And then after taking some analog signal that's been pulse amplitude modulated like this, we would then apply PCM by an encoder to convert these amplitude levels into a sequence of ones and zeros, which we can transmit. We pass these through regenerative repeaters as we transmit these through, say, a wire. And the reason for doing this is when our signal gets transmitted, it picks up noise and it also dissipates power along the way. It loses energy. So these repeaters basically keep our signal going. They amplify it and they clean up noise for us. Some advantages of digital transmission. We have a higher noise tolerance because all we need to do is transmit a 1 or a 0. We can easily remove noise. It's easier to store and it's secure and reliable by the fact that we can encrypt, decrypt, we can check for errors, etc. The issue with this is we require much more bandwidth. For example, if you look at an analog wave compared to a digital wave, these sharp spikes in our pulses have very high frequencies, which means that we will require a very high bandwidth. Another reason being this criterion here. So to sample an analog signal, we always have to be sampling at twice the bandwidth or the maximum frequency of our analog signal. The reason for this is in the digital frequency domain, you will have your signal repeating every fs. So if our message has a bandwidth that is wider than fs on both sides, so this being twice of your bandwidth, then we will get this overlapping occurring, and this is called aliasing. Aliasing is not desired because then we'll have this addition of these two waves creating some sort of distorted frequency output, so when we convert back to the time domain, we're not going to get the message that we want. In practice, we also include a guard band just to make sure, be extra sure that this phenomena doesn't occur. Cool. So then looking at ideal sampling, if it loads. Hello? We might have to come back to this. Yeah, copy and paste it. That's weird. Might have to move on. I'll try. So the main things were, oh, there we go. Okay. So the main things were we have to sample at a rate of 2 times the maximum frequency. Right. And then we have ideal sampling. So in the ideal case, the way we sample, we want to be taking these impulse samples. So at a very specific time, we look at the amplitude of that wave. So that is denoted by this formula here. In reality, though, we can't sample at such a minute time scale. So we actually sample using rectangles. And this is called pulse amplitude. And this is called pulse amplitude modulation. So we're just looking at the amplitude at each of these time intervals, which is denoted by t. And the time period between different samples is denoted by ts. So this here is the formula for the modulation, and this being the rectangular function that we are using to take these samples. In the time domain, we will get a repetition like I explained over here, but the difference is we'll have this overlapping sync function, and this will basically cap the amplitude of the repeating bands. Cool. Some other forms of pulse modulation, pulse position modulation. What we're doing here is we're taking some output, some amplitude. So the amplitude here is 0. So that means that the position of this peak will be halfway in between this period. Whereas when we have a larger amplitude, we will have a peak that is somewhere towards the end. So if I draw something like this, if we have, looking at this one, if we have a high peak, then we'll have a peak towards this side of the band, whereas we have a low peak, we'll have a band closer to that side. Pulse width modulation isn't very detailed, very covered in much detail in this course. Essentially, it's very similar to pulse position modulation, but essentially what we're changing is the duty cycle of our transmitted message. So we have a high amplitude, meaning a large positive duty cycle. A very negative amplitude would mean a very small duty cycle. Cool. So after we've sampled, looking specifically at pulse modulation, after we've sampled, we'll have some sort of amplitude that is still with respect to our analog signal. And we need to quantize this to levels. There's two main ways of doing this. The first one being uniform quantization. So we have some amount of levels L, which is 2 to the power of the number of bits that we have. And what we'll do is we'll take some signal, and then depending on which level it's closest to, we'll just shift that amplitude level to that level there. The resolution of these levels is given by the signal range divided by L, and the actual noise is given by is capped at half of the resolution on either side. The reason for this being, say we get an amplitude here. This is the case of our worst possible error, because we would be shifting by an entire half of the resolution, up or down. Alright. Lastly, SNR for quantization. SNR will obviously improve when we have a larger number of bits. And this is because the distance between our levels will decrease the more bits that we have, which means that we have less error occurring, because for any amplitude there'll be a level that is much closer than when we have less bits. So we can see here that the SNR is directly proportional to the number of bits that we have. And again, it is given by the power of the signal over the power of the noise. Uniform quantization isn't always used. In a lot of cases, we use non-uniform quantization. And the reason for this is, for some voltage levels, we might want a higher resolution than at other voltage levels. For example, the human ear is very sensitive to low amplitude noise or sounds. So when we have a quiet output, we might want to have more resolution there, because the human ear can detect that change. Whereas when we have a really loud output, something loud to our ears is like loud. Even if it's like 2 times loud or 1 times loud, it's still going to be loud to us. So we want more resolution in specific areas. To do this, we've come up with 2 different forms of non-uniform quantization. These are basically different laws that are used in different countries around the world. The first one being mu law, and the first one being A law. The formulas are given here. But they do have the main similarity, which is when we increase our factor, we end up with a larger warping of this quantization. We become more and more less uniform. Alright, pulse code modulation. Pulse code modulation is probably the most important modulation in this topic. What it does is, after taking a pulse amplitude modulated signal, it will convert these amplitude levels into some sort of code denoted by 1s and 0s. After we've taken this pulse code modulated signal, we will then transmit the signal, as explained, using regenerative repeaters. The most important part here is being the decision-making device. If the output is less than the threshold, then it will drag that down to a 0. If it is above, then it will drag that up to a 1. Cool. Other 2 types of source coding. The first one is delta modulation. So rather than, for each sample, rather than transmitting a sequence that directly describes the level, we can just use delta modulation, which tells us, relative to our previous sample, how much did our output change. And this is often preferred over PCM because it allows us to transmit information with much less bits. But the only drawback with this being that it only really works with slow changing signals. When we have a really fast change in the signal, we find that since we can only change our output by 1 level at a time, this DM modulation can't actually follow the signal properly. A solution to this is differential PCM, where rather than transmitting a 1 or a 0, saying it's going up one level or down one level, we're actually transmitting some value which corresponds to that change in levels. So it can be like, say, 5 levels or 7 levels. The way this works is it uses a prediction filter. So this is often some sort of filter that looks at your current output and with respect to some weighted sample of your previous outputs. And using that, it can determine it can determine the rate of change, or it can predict what the rate of change will be in the next sample, which turns out to be quite accurate. Obviously, if you consider more samples, more previous samples, then you will have a better prediction filter. Yeah, there's not much else to say about that one.
So there are sample at a different rate based on the prediction filter's decision.
It won't sample at a different rate. The only thing that will change is the sequence that it outputs. Because the sampling rate is defined by your PAM, right? It samples at regular rectangular intervals, and then what your PCM does is it just takes those rectangles and it creates some sort of bitwise output, which corresponds to that PAM signal.
Yeah, my question was, what is the prediction filter doing to what patterns is it reading? What is it doing to make sure it's better?
Well, we can look at a simple case, like if you have 2 points, this is your current, this is your previous, then if you take the difference between the two, you can kind of predict what the next point will be. Yeah, it's kind of like, if you look at a really small time scale, you can kind of call it linear. But obviously, if we have more and more samples, you might have some more complex algorithm to calculate the next rate of change.
It predicts the next value, and then it has the quantized value which it gets from the PAM.
Yeah.
And then it compares the two, and based on that, it sets the value to either be quantized.
Yeah, it doesn't ever look at the value that it transmitted itself, because then that would kind of throw it off. It would only look at the samples that it's received so far, right?
And then it, the sample it receives, it changes that to the predicted value?
Yeah.
It raises
Yep.
the number.
Yeah. Cool. Alright. So this question is from the 2021 finals, question 3. We are transmitting a signal with bandwidth of 15 kilohertz. The Nyquist rate of this will always be twice of your bandwidth. So we will have a 30 kilohertz sampling frequency. If the Nyquist samples are quantized into that many levels, then determine the number of digits required to encode this sample. So as I wrote earlier, we have the number of levels equals 2 to the power of the number of bits, and we just need to find what value of b corresponds to this value. So doing the calculation, we find that b is close, 16. Yeah, 16. Next, we want to determine the number of binary digits per second required to encode this audio signal. Whenever I'm given a rate, I usually like to write the units out. So for example, if I'm given a rate that I need to be in bits per second, then I might want to find something which is in units of bits per sample, and then multiply that by something with units of samples per second, so that these samples cancel out. So the bits per sample is simply given by the number of bits we have every sample. So this will be our B. And our samples per second is our sampling frequency. So we have our rate is equal to the number of bits times our sampling frequency, which will give us 16 times that. That is, I believe, 480K. bits per second. Is that right? I think so. Alright, then part 4. For practical reasons, signals are sampled at a rate well above the Nyquist rate. For example, CDs sample at a rate of 44,100 at the same number of levels. So to find the same rate, we would just use different values. So we would have 16 again, but this time our sampling rate is 44.1 kilohertz, which gives you some value. Calculator. (705.6 kilobits per second). Lastly, the output SNR of a 10-bit PCM is found to be 30 decibels. We desire the SNR to be 42 decibels. We are asking to find the fractional increase in the transmission bandwidth required for this increase in L, or hence the increase in the number of bits required. So let's do this one first. Find the number of bits required to encode these L levels at an SNR of 42. So right now, at an SNR of 30 decibels, we have a 10-bit PCM, which means our number of bits will be 10. If we want to increase it to 42, we need to add 12 decibels. What I can do is I can simply look at this formula here for SNR with respect to quantization error, and we see that for every bit that we have, we're adding 6.02 decibels, which is roughly 6. So if I add 2 bits, then I will be increasing the SNR by 12.04, which is basically 42. So you want to add 2 bits, which gives us this value here of 12 bits total. Alright, so then, yep, happy with that. Moving on to topic 5. Before I start topic 5, I just want to explain something very quickly to do with the overview of this course. So there's 2 different main ways to transmit digital signals. One is being the baseband, which is bound between 0 and some bandwidth. This is what is covered in topic 5. The other way of transmitting digital signals is using digital modulation. And that's when we want to transmit at some higher carrier frequency, FC. And this is what is covered between topic 6 and 8. The reason why we learn these 2 different methods is obviously because they're both used in this day and age. Baseband is typically used for wired transmission, whereas carrier is used for wireless transmission. Because the whole reason we're applying a carrier is so that we can transmit at some frequency and detect it using some sort of antenna. For examples of wired transmission might be like Ethernet cables, or for example, optic fiber, whereas wireless could be anything like satellites or like telephones or anything like that. Cool, so jumping into line codes. After receiving our PCM signal that we've covered in topic 4, you may want to apply a line code to improve these properties. Self-synchronization being the first one. If you consider the case where we're transmitting a PCM signal with a lot of ones cascaded together, it becomes very hard to tell where the clock occurs or where these samples occur. So line codes, one of the things that they do is they improve this self-synchronization property when we have these long chains of the same bit being transmitted. Other properties is that then allows us to lower the bit error rate, minimize transition bandwidth, and increase the error detection capability. So there's 2 main types of line coding. The first one being non-return to 0. This simply means that for the entirety of the bit period, it stays at the value that it's trying to transmit. So this is non-return 0 because for 1, it stays at some positive amplitude, and for 0, it stays at some 0. Stays at a 0 amplitude. Whereas compared to return to 0, for half of the period, it will transmit the value that it's trying to transmit, and then it will jump back to 0. So what happens is when we have, say, a long chain of 1s, even though we have 1s one after another, we can still tell where the clock is occurring. And that helps us essentially self-synchronize. Another difference is unipolar versus polar. Unipolar, a 1 is transmitted at some positive amplitude, a 0 is transmitted at 0. Whereas polar, you transmit a 1 at some positive amplitude and a 0 at some negative amplitude. The benefit of polar over unipolar is that for unipolar, you will get some average DC value for this line code that is non-zero. Whereas for polar, if you assume for some very long sequence that you have an equal number of 1s and 0s, obviously the positive and the negative amplitude will equal out and you'll get a DC component of 0. The benefit of this is that a lot of baseband channels are often AC coupled, which means that this DC component is being removed anyway. So it's kind of, I guess, a waste of energy. Another thing being, when you have your DC offset, it can often lead to bit errors. So that is the benefit of polar over unipolar. Manchester. In Manchester, you're simply transmitting a high for half a period and a low for half the period when you're transmitting a 1. And when you're transmitting a 0, you're transmitting a low for half a period and a high for half a period. Bipolar is similar to polar and RZ, but instead of transmitting a high every time, when you're transmitting highs in like adjacent highs, you will alternate between a low and a high, low and a high. But zeros will still be transmitted as zeros. Time division multiplexing. So time division multiplexing becomes useful when you're trying to transmit a lot of messages, but you only have access to one channel. So what you can do is you can alternate between sending a sample of each, whether it's synchronous or asynchronous, depends on when you switch between each sample and how long you stay on each sample. And you can see that this is denoted by this sort of clock-looking thing where this arrow is moving between each message with respect to time. We have two different types of TDM. Asynchronous is when all of your messages have the same sampling frequency, which gives you these simple equations. Whereas in asynchronous, we have messages that are at different sampling frequencies, which is denoted by these slightly more complicated equations. Cool. So moving on to transmitting at the baseband level. This is the general overview of this transmission. After we've received a PCM signal, we are going to line encode to improve self-synchronization and bit error rate. Then, because we are transmitting with a baseband, we are limited to some bandwidth. So we can't actually transmit perfect square waves. These will be bandwidth limited. So these sharp peaks will be slowed down and will have some sort of lower frequency shape. After passing through that, we will transmit the signal. It might pick up some sort of noise, some sort of interference. This is a filter that we cannot control. It is a result of the environment. And then lastly, the receive filter will try to filter out some of that noise. Lastly, we pass this through a decision-making device, which takes these pulses that we get at the end and decides whether we tried to submit a 1 or a 0. Cool. So the main thing we're going to look at is this transmission filter here. The pulse shaping is very important when you're trying to minimize what we call ISI, which I will get to on the next slide. ISI being intersymbol interference. And then last thing on this slide, binary versus emery. This is a new term that we've come across. Binary is transmitting using 1 bit, so there we have 2 to the 1 levels. Emery, we have m bits or m levels. So then we have m bits, so then we have 2 to the m levels. For example, if we have 8 array, then we would have 3 bits. Whereas binary is 2 levels, so we have 1 bit. Cool. Moving on to ISI. So ISI is a consequence of when we have band limited channels. Because they're band limited, if we have 2 pulses that are very close to each other, then we will get some sort of overlap, which causes distortion when we demodulate at the output. So in terms of minimizing ISI, we get the minimal ISI when we have a frequency response that is what we call a brick wall. It's just flat. This is because this is saying that we treat every single frequency the exact same. If we had some sort of varying frequency response, that means we would be treating different frequencies differently, hence resulting in this distortion in ISI occurring. So considering the fact that this is in the digital frequency domain, to get a brick wall response between our sampling frequencies, we need a rectangle, so that we have repeating rectangles that altogether make up your flat brick wall response. So to achieve a rectangular output for your frequency response in the time domain, to do that you're going to need to somehow generate a sync function, which is very hard to do. So in practice we don't actually create sync functions to transmit our pulses. We instead find something that is a bit easier to do. In the optimal case, we would opt for a raised cosine pulse, which looks something like this, denoted by these functions. And essentially, this is the shape of the pulse that will give us the frequency response that looks closest to a brick wall. Yep, so it's our second best option after the sync because we can't actually use the sync function. All right. Then we have I patterns. I'll just draw an I pattern. So on the oscilloscope, you probably would have done it in the lab, but we generate some sort of I pattern. Great. And we find that we transmit with less interference, intersymbol interference and distortion when we have a wider I. So the width of the I corresponds to how much ISI we have. The slope corresponds to how fast we are transitioning. Obviously we want a higher transition time to become less susceptible to noise. And the height of this I refers to the noise margin, which is how tolerant we are to noise being introduced to the system. Yep, so in general, the bigger the I, the better. Lastly, frequency division multiplexing. So this is essentially when we send multiple signals at once by modulating signals at different carriers. So we might multiply one of them by some carrier, another carrier, another carrier. Often we put in a guard band to prevent overlap from occurring, or in other words, aliasing. And then at the demodulator, we will apply some sort of bandpass filter to simply look at one of these messages. Cool. So we'll move on to a question. Design a TDM system that will accommodate for two 2.4 kilobit per second synchronous digital inputs. And an analog input that has a bandwidth of 3 kilohertz. Assume that the analog signal is sampled at the Nyquist rate and converted to a 4-bit PCM word. So we need to draw a block diagram that demonstrates this design, and we need to indicate the data rate that we get at the inputs and then at the output. So if I draw a TDM system, we have something that will look like a clock. These digital inputs will be fed directly to this TDM system, but we need to process this analog signal to turn it into some sequence of ones and zeros. So to first do this, we need to convert our analog signal into PAM. So to get a PAM signal, we need to sample using rectangular pulses. And then, oh wait, first of all, my bad. No wait, it's all good. So what is the frequency that we need to sample at? 6 kilohertz, yeah. So we need to sample at twice the bandwidth of our input signal. So we need to sample at 6 kilohertz. And then I'm just going to chuck this in. We also need to quantize that so that our PCM can directly convert this into bits. So our PCM will be done through some sort of encoder, which will be 4-bit, specified in the question. And that will give us some sort of sequence of ones and zeros, which corresponds to our analog input. And we'll feed that in as well. So to find the rate for this analog stream, we know that these are 2.4 kilobits per second. We need to find the rate for this one. As we did in the last question, where is it? We found that the rate is given by the number of bits per sample multiplied by the sampling frequency. So we can do the exact same thing here. So our rate is going to be equal to the number of bits, which is 4, multiplied by our sampling frequency, which is 6 kilohertz. Great. So that will give us a total bit rate of 24 kilobits per second. So in total, when we have asynchronous TDM, our data rate will be the sum of each of these individual data rates. So our total rate will be 2.4 times 2 plus 24, which gives us a total rate of 28.8 kilobits per second. Cool. So that is our TDM system. Yes?
Did we assume it was asynchronous TDM?
Well, we know it's asynchronous because, oh yeah, we are assuming it's asynchronous. Yeah, we don't exactly know the sampling frequency of these, do we?
I don't think so.
No.
We do on the bit rates.
Yeah.
But another question.
Yes.
It says synchronous digital inputs. What does the synchronous mean?
This would just be saying that these are being sampled at the same sampling frequency. Yeah, obviously this will have to have a different sampling frequency because we need to sample at twice that bandwidth. Yep. Cool. All right. And then question 4. A DPCM signal is to be transmitted using a baseband polar return to 0 line code using an RF transmitter. The RF transmitter uses a binary DPSK modulator. The sequence of bits that we're trying to transmit is right here. So for part A, we are asked to sketch the polar RZ line code for this bit sequence. So if I do 0, 1, 1, 0, 1, 1, 1, 0, 0. For 0, in polar, we're transmitting a minus, which goes back to 0 because we're doing return to 0. For the 1s, we're transmitting a high and then a low. 0, transmitting a low. 1, transmitting a high, 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 and then a low and a low. So that is our polar return to 0. Part B. Explain one useful characteristic of this chosen line code. So as we went through earlier, polar line code is usually better than unipolar because we have an average DC component of 0. And another thing to note is that it's returned to 0, so we have some sort of self-synchronization going on. Alright, and C. What is the approximate bandwidth of this baseband pulse signal? So if we consider a bit period of TB, we have a change in the output every half TB. So we need to be sampling at twice of that rate. So if our original frequency for a non-return to 0 line code is given by 1 on TB, then our frequency for return to 0 would have to be twice of that. So that is given by 2 on TB. And that is our approximate bandwidth. Cool. Does anyone have any questions? All good? All right. I will now hand over to Otto then to explain digital modulation.
All right, give Jackson a hand. I would like to once again thank you very much, Jackson. This was quite frankly not going to be possible without him. So, without further ado, let's get on to this. Okay, so where are we? We're topic 6. Topic 6. Right now we're talking about digital communication system overview. We're going to be talking about the digital bandpass modulation stuff. So, as Jackson mentioned previously, this is going to be somewhat aligned with on our frequency plane, this little block up here that we've modulated. Okay, so very much looking at channel decoders and such. Let's get it moving. Here we are. So here's some information. Quite frankly, as we've seen in analog, we can modulate stuff. That is very cool. We kind of just multiplied by a carrier, and we have this very important note of the energy of every bit, because that is going to be very important, especially in our comparisons for noise analysis. So energy of a bit is, quite frankly, just the average, I guess, average power amplitude of that bit. Okay, so that's how we go ahead and divide this, considered by that integral. And let's just start rattling off some modulation techniques. So we have binary ASK, which is binary amplitude shift keying. So all we really do is we multiply it by a carrier. So we get our binary values, which are 0s and 1s. Let's go over to the right. Oh my gosh, can't even use my own device. There we are, okay. So, typically we got 0s and 1s. By doing a binary amplitude shift keying, we're really just looking at this and multiplying it by the same cosine. So, when we see a 1, we see the sinusoid, quite frankly. There are some nice finicky details just concerning the power spectral density, just so you know, that's what the PSD stands for. Not too much for us to run through here, but let's keep it moving. We got frequency shift keying, which is going to be supplied over here, where we actually swap between two different frequencies whenever we display a 1 or a 0. Some very cool things just have to do with certain conditions for continuous phase. My gosh, it's a little laggy. I'm pretty sure it's because I've done a lot of scribbles on it, and so it's not the happiest. But we'll just give it a little second. So essentially, for a continuous phase, all we really want is to know that the difference in frequency that we're working with is going to accommodate for, I guess, the changeover, right? So the difference in the frequency should be equal to some multiple of your, I guess, your bit rate, okay? And so what that means is if I'm going to have 0s and 1s and 0s and 1s, I have a frequency here, and then it's going to match up with my next frequency
and maybe go faster, and then still match up with my next frequency and then go slower and all that jazz, okay? So it's all about these matching up on point, and there's a couple of reasons why we want to do this. It helps us detect it, quite frankly. So you can imagine something we would have seen in our phase shift keying or something like that, your quadrature phase modulation. You would have some kind of thing going, actually I'll draw that a little better, some kind of thing going like this, and then, you get a change in bit, and then now it's looking like this, and then you get a change in bit, and then it's looking back like this. These have very, very abrupt changes in our signal, which when we try to just detect between them can lead to some bit of noise and error, because quite frankly we can't change voltages very instantly, and so you get something of a delay between them, which not the nicest. So moving forwards, this is the condition for it, because it allows some integer number of oscillations between your two frequencies to be observed, so they can meet exactly on point. Okay, so moving forwards, we recall transmission bandwidth. We saw this a little while ago. It is very similar to our Carson's rule, I believe. And yeah, there's not too much more to talk about there. We know that we have a change in our frequency given by between 0 and 1, very, very similar to our frequency modulated analog signals, okay? But now we're just doing it digitally. That's all it is. So, moving forwards, as I mentioned, easier demodulation, and you minimize the bandwidth as well. You can imagine sudden changes require very high bandwidth to analyze properly, right? So, next up we have minimum shift keying. So, we're going to go ahead and think about just frequency shift keying, but with the minimum frequency differences that allow orthogonality. So, this, I believe, is going to be, we use this rule. Give a sec. All this really goes ahead and looks at is you have your 1 signal and your 0 signal, and we're going to apply the smallest change in frequency, which is going to be observable in the same sense. So if we go ahead and apply that to what we have previously, we note that before we have transmission bandwidth given by, let's try and find it, I believe, so I believe the minimum shift keying is going to be referring to, you have your central frequency, we want to bounce it up or bounce it down, and these two levels, so this is C, this is going to be plus delta F, this is going to be minus delta F, and it just really allows us to, I guess, experience the smallest change in our frequency so we can use the smallest bandwidth possible, okay? Because you can imagine our total bandwidth is going to be from top to bottom, so just 2 delta F, you can imagine. All right, good stuff, good stuff. So moving forwards, more content, we got binary phase shift keying. Binary phase shift keying, let's go ahead and identify really what that means. It is when we have our immediate phase bumps, okay? So that's what we were talking about before, something that we don't like in frequency shift keying. We have it in phase shift keying, where we add a bonus pi, or we just make the damn thing negative because it is just the same. This has a bandwidth of 2 on TB. We could go ahead and talk about why such things happen, quite frankly. If you have a, let's do an example. We have a 1 here, and then I'm going to go a 0 here. Now, I know that this entire region, I'm going to call that a time called TB. Now I need to determine what kind of bandwidth I can use in here. So, bandwidth required is going to need to identify a difference between these two types of signals, right? And so, something that we could try and do, if we use 1 on TB, then sure, that gives us something that matches with both of these. However, it's not really going to observe the change very well, especially in here. We need to observe at a slightly higher frequency, and we can relate this a little bit more to sampling. If we go at twice the rate, we can see that, okay, here we have 1, here we have 2. It identifies, yes, there is a high here, yes, there is a low here. So that's one of the big advantages of bumping up our frequency. It lets us see things a bit more clearer, okay? So we use 2 on TB. That is a thing, all right. Now, moving forwards, we have QPSK. So Q, in this sense, I believe it's, usually we refer to as like quadrature, which in phase, in quadrature, I think for this one, a bit more specifically, we like to think of it as quadri, just because you're splitting into 4. So using 4 different phases, yeah, what's up?
So for the bandwidth, are you just like have the frequency for the 1, frequency for the 0, which are both 1 over TB, and you're just adding the 2 together to get 2 over TB?
Kind of, yeah. So you're pretty much identifying that, this is about this scenario, right?
Yeah.
Yeah. So the idea is, to my understanding, that you need a higher, I guess, bandwidth in order to properly, I suppose, identify the modulated signal. So you have these, however, they would be pushed forwards, modulated extra, and so you get, sorry, just a sec. So from 0 here to, I guess, 1 on TB, this is where all the action happens, but you know on your frequency diagram, you have -1 on TB here, everything gets modulated, so then you end up with your 2 pulses out here, so you get a bandwidth of 2 on TB. So that's like the mathematical idea behind it, and then we can try and apply that just to how we see it over here, needing to do some number of revolutions, and then how we analyze differences between those. What's the minimum bandwidth needed for that, right? Yeah, hope that somewhat helps the understanding.
I don't kind of get how that relates to your reasoning for how you said that you want you have the frequencies for the 1 and the 0 to be different.
Oh, no, sorry, no. Not the frequency is different for the 1 and 0.
I thought that was
No. That's like seeing the highs and the lows, right? Like the transitions between them, I believe.
They both at the same frequency, right? 'Cause
Yeah.
there's
The 1 and the 0 aren't the same frequency there. Yes.
Yeah,
So,
you mentioned something.
sorry, I must have misspoke. That is my bad. All right. So, quadriphase. We use 4 different phases. Typically, we like to split it up along the pi and 4 multiples. So we end up with, on the diagram, a little x plot with these 4 phases. It mainly is used for error correction. The reason why we split it up like this, so we can just say, oh, my point for this bit is in this quadrant. Okay, so then I'm going to take it as this value. It just helps us go ahead and go about it. You could rotate it, could do really whatever with it, but yeah, all right. That is what quadriphase shift keying is. Then we can look at differential shift keying. Differential shift keying is very much, okay, I'm going to refer to this piece of data in reference to the previous one, and then just relatively move forwards with that. Now, couple things with this. Just understand this right here is the XOR, I guess, gate. So you're saying that your transmitted encoded signal, EN, is going to be the XOR of your incoming signal with the previous encoded signal. Okay, so let's just do a little example. If I have 1 0 1 1 1, and I'm saying, okay, my encoder is going to begin imagining there's a 1. What is the encoded thing going to look like? So it begins thinking there's a 1, it sees a 1, so there's no change, sees a 0, so there is a change, there's a 1, there is a change, there is a change, there is a change, there is no change. So this would be the encoded versus the unencoded, just the incoming signal. Okay, hope that helps. Let's keep it moving. So here's just the general ideas on how you would construct these different modulation, filters. Well, not really filters, just your modulation systems. So you have your binary phase shift keying, where you go non-return to 0, so that's your 0, then your 1, and you're going to be multiplying this by, oh no. Okay, let's not be able to see the picture for a couple seconds. So essentially, this is how you're going to make them. There's not too much to talk about here. If you understand what they're going to look like, you can usually work together and say, okay, this is going to be this much off phase. You can break it up like these, move into different modulators. But there's not, I guess, too much on it. Like, you have very special threshold devices that make decisions, and on occasion, when you need to use multiple bits, you will definitely need series to parallel converters and parallel to series converters, just because, yes, what's up?
Could you explain why we're multiplying by some oscillating frequency?
Is this for the QPSK?
Yeah, for any of them.
For any of them, okay. So, for the demodulations, why we're multiplying by the oscillator. So, quite frankly, whenever we have these digital signals, just remember we are talking about digital modulators. So on the frequency domain, they have been shifted. They have been shifted by some quantity FC, I'm going to call it, onto a carrier. Now, what we want to do is we want to say, okay, well, I can't really reach you and say that, okay, I know this frequency, I'm going to talk about very minute spaces. Instead, I want to drag it back towards the baseband, and then I can start just smacking around with some more math, which is going to lend back into the baseband demodulators. Okay, so there's typically going to be some kind of line you can draw in most of these. That'll just be, okay, here's where we're going to convert it back into a baseband, and then just do the baseband kind of thing. So in this scenario, QPSK, quadriphase shift keying, we go ahead and we want to get them out of the thing. So just recall, you have this plot, these 4 values. What they like doing is saying, okay, let's split it into a vertical and a horizontal component. So what that's going to do is, if I multiply by a cosine and I multiply by a sine, I end up with 4 different options. Either I can have a cosine plus a sine, which is going to look like the first one. You can have a cosine minus a sine. You can have a minus cosine plus the sine, and then a minus the cosine minus the sine. And this really just identifies all 4 quadrants. Okay, so this is how they think of it. So you multiply by the oscillator, your respective oscillator, mind you, so you can isolate whatever your cosine term and your sine term are going to be in terms of their amplitudes. And then by sampling these after a low-pass filter, we can isolate the positive, well, really just the sign of your cosine and sine, if that makes sense. Sine with a G, yes. Okay, and then parallel to series converter. You're happy, right? Good stuff. Let's think a little bit more on coherent and non-coherent detection modulation. So, as per usual, we like coherency. We don't like coherency because it relies on us being coherent and in phase with whatever carrier. So let's think about how we can go ahead and do it without coherence. So non-coherence. Let's do this. Okay, so we have binary phase shift keying. That is not phase, that is frequency. That was my bad. Binary frequency shift keying. To detect it, we have the 2 frequencies. So we want to bandpass for those 2 frequencies. Just recall, frequency plot, you're oscillating between not oscillating, you're bouncing between these two frequencies, so F1, F2, which are holding your data. So if you bandpass between the two, you should be able to, okay, I see something very high in this one, envelope detect that, and then potentially hit a threshold with it. Doesn't really matter. You sample and you run it into the comparator. So by comparing these two levels of your two different bandpasses, you can decide by some manner of threshold inside your comparator whether it's going to be a 1 or a 0. Okay? Sound fair enough? Good stuff. Then we have the amplitude shift keying. So let's think about this one. This one, as per usual, you get 0 and you get something that wiggles. If we go ahead and we tune it to the carrier frequency, we should see that it either wiggles or doesn't. And so you can make a decision-making device with a threshold to say if it's 0 or 1. Let's go ahead and try and race through these so we can go ahead and ask some questions. So we have M-ary signaling. So M just really stands for a number if we want to push past using just 2 levels in our binary. Something goofy, which I'm pretty sure they get wrong in the slides for the course, is they refer to M-ary as like, there's some point where they go like 2 to the M, where it's very much questionable when in all the cases they're just referring to M. M in this course is purely going to refer to the number of levels. So binary is 2-ary, which is a little bit silly, but yes. If I want to use 16 values, or in other words 4 bits, I have to use 16-ary. Good stuff. Let's keep on moving. So we have 2 different rates to identify. We have the baud rate, which is the number of signals per second, and we have the bit rate, which is the number of bits per second. Now, for different types of, I guess, shift keying, you can also apply these multi-leveling, I guess, signaling techniques. So you have M-ary ASK, so amplitude shift keying. We now have multiple levels we can shift the amplitude to. M-ary phase shift keying, there are now multiple phases we can shift to, which one example of that was QPSK. All right. Not too many things of note. You just know that you have to divide your phases up. You have to divide your total amplitude up. Yeah. All right. Let us hit the example. So previously, yep, what's up? Oh, sorry, I didn't see it.
Okay. So with the gray coding in that diagram.
Right, yes.
Is there like a set sequence?
Okay, so fun thing with gray code, there's exactly 2 ways to do it. I don't know. There's you can do it, if there's n bits, there are n ways to do it, which is a little bit screwy. So the way that I like to do it, to get a nice sequence every single time, we're going to go on a little side tangent. I believe it's gray with an A. Gray code, don't fact check me. So gray code, if I usually like putting 0 at the first and then 1. There we go, that's 1-bit gray code. If I want to make it 2-bit, I add a 1 on the end and I just reverse what I had before. So I'm going to go 1 1 1 0. Now I'm going to do the same thing. So I put a 1 on the front, I have 1 0, and now I'm going to reverse everything else, and I actually ensure that I am only changing 1 bit at a time. Okay, so there's a number of ways that you can go ahead and figure this out. The only issue with this kind of method, actually no, there are no issues with this method. Are there? No, I don't think there are. There are no issues with this method. I was going to say, when you want to go from your last one back to your first one and make a bit of a loop, there's actually no issue because you just get rid of the last one, which is your reversal. Okay, so it always works in this method. I like using this method. You can take notes. The steps were do 0, then 1, then add a 1 on the end and reverse, add a 1 on the end and reverse, until you have as many bits. Okay, so that's one way you can do gray code. It always works. Trust me, please. But yeah, the idea of gray code is you're only changing 1 bit at a time, which this permits. You get as many values as you get in binary, which makes sense. And yeah, does that answer your question? Fantastic. All right. So back to the question. That was a nice side tangent. Thank you very much. So we have we're going off of the same question that Jackson was working off before. We're going to do the last three parts. Okay, so first of all, we have differentially encode this bit sequence, assuming an initial reference bit of 1. This sounds very similar to a question we just did, so without further ado, let's do this. D, we begin with a reference bit of 1, and we have the number to encode. So here is the sequence to encode. I believe I wrote that out correctly. And let's just hammer this through. Reference bit is 1. The bit I see is a 0, so I got to change it. That's a 1. Got to change it. That's a 1. Stay the same. Change it. Change it. Stay the wait. Sorry, I forgot. You change it. Wait. Am I losing my? Yes. Yes. Or yes.
1.
So we change it. We change it. We keep it. We change it. We change it. We keep it. We keep it. We change it. We keep it. There we go. That's more like it. How do we feel about that? Okay, good. All right, let's move forwards. So, just applying our XOR, moving through it. Okay. Part E, we're going to determine what is the purpose of differential encoding here. Well, there are actually there's a couple different reasons we can choose to differentially encode, just rather typically. For this case, any ideas?
Well, since you're looking at the change relative to your previous input, the phase difference is going to be relative to that previous input, right?
Yes. So Jackson makes a fantastic point here, and the idea is that if I have this in this is polar RZ line code, so since it is polar, base around 0, return to 0, so you're going like a 0 is a low, then here half the way, then a 1, then so forth. By having it like this, you have a sorry, give me just a second. You're relying on changes in phase, okay? You have a change in pretty much a change in phase between these two, if you were to look at it in any other way, which usually we don't like to constantly change it. We are changing it relative to whatever value we see there. However, in the differential encoding, if it stays the same, then we just put pretty much, okay, nothing changes. We don't need to transmit something, right? Does that kind of match with what you were saying? Yeah.
Yeah. You can also relate it to like a lot of these demodulations use phase octave, which looks at the absolute phase of your sequence. If you use, that can be an issue. So with differential encoding, it becomes the relative phase with respect to your previous input.
Right. So it's the conversion from, just for anyone who didn't hear online, it's the conversion of absolute phase as a comparison to relative phase as a comparison. So we can understand that, okay, a 0 might have a certain phase associated to it. A 1 might have a certain phase associated to it, just in modulation. However, when we go ahead and we check by encoding it differentially, we can say, okay, did the phase change? Sure. If it did, then I'm going to apply it to my new system and I know what's happening there. There's no bonus bits of information floating. It's all dependent on whatever my reference bit is. Okay? So that way I keep rather consistent in my measurements. Going all right? All right. So very much for, I guess the words we can use here are recontextualizing the phase analysis of bits from absolute to relative. All right, good stuff. Now we have part F. All right, so this question says, sketch a diagram illustrating the features of the DPSK waveform for your differentially encoded bit sequence. So, quite frankly, I'm going to go ahead and still have the polar return to 0, and we're seeing that there is a modulator. Let me just think about that. Oh, differential phase shift keying. Okay, fantastic. Let's do this. So we're going to see phases change. So I begin with a 1. So I'm going to call a 1 like this. This is 1. There's another 1. There is a 0. And I can just set it out like this, so I can just chuck in all my 1s and then all my 0s. Very much concentrating on this. All right, and there we go. So this is one way we can do it. Mind you, I've tons exaggerated whatever the frequency would be. I really just do that so that it fits nicely. Yeah, all right, good stuff. That is that question. There is now another question. So let's go ahead and race through this one. So let's do this. Part A, let's think about part A. What does part A say? We want to find bandwidth of a transmitted signal given binary ASK of the above. We're given a bit duration, and we also have the frequency over here. Okay, so that's probably that's the frequency of the modulator. All right, so if we actually just double check the above, we actually determine that the binary amplitude shift keying, we have a bandwidth given by 2 on TB. As we mentioned previously, there are ways that we can derive that which are very much attached to just the modulation of it and the difference between the two different modulated ends of that term, and so we know it's going to be 2 on TB. Oh no. Okay. 2 on TB. Fantastic. We can calculate that in our own time. I'm going to choose not to. So, part B, we're going to ask, okay, we're going to change M from 2 to 4, and now we're going to define our amplitudes with a mapping. Okay, so this is kind of going to be a question that builds up and gives us more information about it along the way. So remember, M equals 4, we're going to need 4 levels, and we're using amplitude keying. So we're going to determine the amplitudes. So does it also want us to, yes, it wants us to plot the waveforms. Sorry, I've misread. I've looked at C instead of B. So plotting the waveform in binary ASK. So for 3 bits, we're going to go moving, 2 bits, not moving, 1 more bit moving, then 2 not. So 1, 2, 3, 1, 2, 1, 1, 2. Fantastic. All right. Now we're going to use 3 levels. And the way we're going to define that is just going to be on this little table. We know there's a 0. Fantastic. And then level 1 is going to be A. Level 2 is going to be 2A. Level 3 is going to be 3A. Now, mind you, these are not just levels as such. They need to be wiggling. So we can just draw wiggling things inside them of varying heights. All right, so this is how we can just identify. But mind you, for this question for part C, it also wants us to map them to binary symbols. So we like to use gray code here. We typically like to use gray code for symboling, as we would have seen in the lab. So I'm going to go 0, 0, 0, 1, 1, 1, not 1, 0, and 1, 0. Okay, good stuff. Let's keep it moving. So we have question D. What is the average power transmitted using 4 ASK? So the concept we're going to use here is a little bit of probability. We don't know the most about this system, so we're going to assume that every symbol has an equal probability of appearing, okay, from the 0th level to the 3rd level, okay? So we say that the P average is going to be the average of our average powers, right? So 1 on 4 times the sum of P I equals 1 up to 4, which is going to be 1 on 4 outside of 1 on 2 times A times 3 squared plus 2 squared plus 1 squared plus 0 squared. Bam, bam, is going to give us like 704 times a squared. Should be an a squared there. 704 times a squared. All right, good stuff. That's how we'll determine average power of this system. Now, mind you, don't let this fool you by saying that, okay, well, this means it would need more power than a binary amplitude shift keying, because a value could be cut into 4. Just depends on how we go ahead defining that. So that's a little bonus bit. We have 4 more parts. This is a chunky question. So part E, let's read it. Give the block diagram of the quadrature phase shift keying generator. So as per usual, quadrature phase shift keying, we want to get something that's going to turn these 4 bits back into binary. Okay, so as we mentioned before, we want to split it into the cosines and sines, those different values. So we're going to just bump them up here and here. This is going to be multiplied by a cosine. This one is going to be multiplied by sine. So 2 multiplications here, and typically we put an oscillator, and a 90-degree phase shift for that. So that gets us most of the way. As we saw in our diagram previously, we like to chuck in a low-pass filter, just so that we do not, I suppose, get a super high frequency out of them. We would just want to get what's low with them. And that gives us pretty much just the amplitudes of the sines and cosines that make up our quadrature. So we need to make some manner of threshold, threshold T, so thresh, or rather decision maker, and then it's going to go into some manner of, because mind you, this is going to be 4 values, we need 2 bits for it. The top one is probably going to be our cosine value, bottom one's going to be our sine value. So instead of doing some manner of adder here, we need to do a parallel to series converter. So we can chuck in this bit, then that bit, this bit, then that bit. So we understand it a bit better. So this goes in here, this goes in here, and this is parallel to series converter, and this is our output. Good stuff. All right. Any questions with that kind of model so far? Very straightforward. Good stuff. Next up, we have part F. All right. So consider binary energy per bit to noise power given in this ratio over here, given by 13 decibels. Calculate the average bit error probability PE. So mind you, this is for binary phase shift keying. So binary phase shift keying, just note that they go from here to there. So there's actually, did they mention anything else? That's how it works. And so you have a bump difference of 2 times the amplitude between different signals. Okay, so it's a very big difference. And to overcome that, your noise signal very much has to bounce like more than a whole amplitude of your signal, rather than typically half the amplitude of your signal. Okay, and so as we go about this, typically we like to just use probability. Couple notes is that your Q value, if I go Q of Z, is actually going to be equal to your probability that your little z is going to be greater than your big Z, as we refer to this on the Gaussian probability kind of chart, which they do supply you at the bottom of your exam papers, mind you. Big table of values. Next up, other things to note is we got this EB on N0 equals 13 decibels. Mind you, this is a power ratio, so we're using 10 log 10. So if I go into my calculator, I can actually say this is going to be equal to 10 to the power of 13 on 10 in terms of linear units. So 10 to the power of 13 on 10 should give us something near 20. Yep. Ish. Good stuff. Now, we go back into what is the probability of error. Typically, we like to go ahead and say that our noise power is going to be the standard deviation, rather, the square root of our noise power is going to be our standard deviation of the noise, okay? And so we can determine the number of standard deviations of noise above which we need to produce an error. And then we can tie probability to that. So that's how we're going to work through this. They do supply us with the equations in the course as for how we derive it. I do know for quadrature phase shifting, they go ahead and say that the noise power is equal to N0 T on 4, where T is your TB, your time of your bit. And they say that the signal power is going to be something like AC squared T on 2, or something of the sort. We don't need to really worry about that too much. All we really need to think about is, okay, we got this. We know that we got to actually bump to, I believe, almost an entire signal. But determine your thresholds, those you would like to actually determine the theorem for that. But just know it's going to be equal to 2 gamma, is it B that they use there? Yeah, gamma B. This is the value that they assign to the probability of an error for your amplitude, your phase shift keying, binary phase shift keying. So you get Q of, there's meant to be a square root there, square root 2 gamma B. Let's just multiply this by 2, get a square root. It is going to be 6 and something. So Q of 6.32ish. And if we want to double check, something we can do is run to the bottom of our exam paper. It has the table of values. It has a very, very extensive table, especially because looking at something that is 6.5 standard deviations above the mean is going to be absolutely minuscule, okay? But still, in terms of transmission, somewhat notable. Let's go ahead and move on to part... Gee, there's 2 parts left for this.
I think it might be good to move on.
Potentially.
We
Let's just race. Let's race through it. So, minimum clock frequency for the PAM signal. We know that it is moving, TB is given by a certain value. We need a clock frequency. We're going to go ahead and apply, I believe, the Nyquist frequency to be able to sample that. And then cutoff frequency to preserve amplitudes is actually going to be half of that. Half of your Nyquist, so it's actually just the same frequency, because that's just recording the amplitude information rather than any manner of phase information. Okay? Let's move on to noise in digital communications. AWGN, I believe this was in your labs. It stands for additive Wyatt Gaussian noise. Gaussian, according to Gaussian distribution. Wyatt, it is equal across all the frequencies, and then additive, you can just add it very linearly to different things. Mean of 0, variance of sigma squared, given by this. And yeah, bit error rates, optimum detection. So optimal detection is considering, I believe, the type of filter you're applying as an impulse to be able to detect it at the output. Okay, so it's just a whole manner of transfer functions, just like cascade, your levels, okay? Levels and probability, that kind of stuff. Here we have the receiver structures. There's really not too much to them. Once again, you multiply by your respective modulators, and then you integrate and dump sometimes. It's not too much to talk about here. Probability of error, as we mentioned, we want to turn it into almost a z-score table, but we like using Q. because we're talking about thresholds being bounced upwards. And we see that there's a ton of different formulas for each of these. Noise in digital communications, yes, we see grey code once again, and we have this general workshops question. Quite frankly, this question doesn't offer the most insight. You're really just plugging in numbers and getting a bit of a feel for it. We know that M is 16, log base 2M is the number of bits per symbol, which is given by beta. If it's 16, we know that's going to be 4. Bit error probability, we just need to plug into this equation. There's really not too much more to it other than don't forget that your decibels is in terms of power, so 10 log base 10, right? And then they want us to compare, and the idea here is the idea of, okay, how do the two different bit error rates compare to each other? Let's move on to topic 8 very quickly. This is likely my favorite topic, mainly because it's got matrices and a bit of idea on how you can code and actually fix errors. So there's a bit of jargon in terms of information and entropy. It's very much just the basis of, okay, how does this idea work? How do we minimize the loss of information? And then how we can talk about probabilities of errors in terms of matrices. So without further ado, let's move forwards. And the main things we're going to be talking about, I believe, are channel capacity. So let's think about this. Shannon's theorem, which is to determine the capacity of a noisy channel, is identifying the amount of signal you can push through depending on the levels that you're working with before it gets too bad. So the idea is you have a certain bandwidth and then a comparison of your signal power to noise power. Mind you, if your noise power was very, very tiny, sure, your capacity bumps up tons. You can get tons of information through that thing. But otherwise, you can't really. So moving forwards, source coding, the idea is that you can compress symbols into certain, I suppose, binary values and really just maximize the efficiency of your channel. You can imagine if you have a probability of sending a certain code like this, and this is like 99% like probability of that happening, you're probably going to want to just represent that with 1 bit. And the reason is, if I send 5 bits every single time I need to do that, if I just send 1 bit instead, that's going to be 5 times faster. That much more efficient in terms of the number of bits that you need to send there. That's the general gist for source coding, and so you have certain measures of what you should do there. Okay, so the average code length. Huffman codes are used to determine the minimum average word length for situations like this. So, I suppose we should keep moving. Error protection, block codes. So, essentially, what we like doing is we want to generate certain matrices that allow us to transmit certain values as codes, and those codes can error correct themselves within certain boundaries, or error detect within certain boundaries. And so the whole thing about detection and correction, Hamming is the GOAT. So Hamming distance is the number of bits different between 2 different code words. Okay? Hamming distance between code words is very important because it tells me, okay, how many errors do I need in this thing before I can't tell? Wow. Okay, so you can imagine if you have one difference between a code word, then, a Hamming distance of 1. If I have an error, I'm immediately telling myself that it is going to be something different. I know it's going to be a different code word that I see after transmitting, which is a big problem because it's the wrong data, full stop. However, if my minimum Hamming distance is 2 per se, then having 1 bit different, I know that there's something wrong, but I can't quite tell what it is. I can't quite tell what it is that is wrong. There's going to be at least 2 different symbols that are going to be close to that value. However, if I have my minimum to be 3, so in other words, TC is going to be 1, then that means if there's 1 bit error, and I assume that it's a 1 bit error, mind you, I have to assume that it's a 1 bit error, I can say, oh, it's closest to this word, and therefore collapse it onto there. All right, good stuff. Having bounds, having weights. Having weight is the number of ones. Having bound is the maximum number of code words allowed in a block for a given error protection. So your quantity of error protection is very much related to your having distance for your D minimum. All right, then you have repetition coding, which is, not going to lie, kind of just bad because you're relying on error probabilities and you need to submit it like n-1 more times, just unnecessarily. Bad code, don't do it. But they can ask you about it. All right, next idea is single parity check codes. So you can add on a bit as a parity check so you get the same, I guess, modulo 2 Hamming weight onto your code words. And all that really does is say that, okay, if there is an error, just one error or some odd number of errors, then I can tell that, oh, the sum of my bits is not divisible by 2, and therefore there has to be an error. So we can build it up this way. You can, heck, add more parity bits, maybe a little bit later, to work with different, I suppose, modular effects, okay, for sums of your bits. Moving forwards, we have parity check codes for single error correction. The big point here is correction. We make generator matrices, we make the receiver matrices as well, and what they do is they allow us to convert any of these, I suppose, 4 code words any of these 4 data words into code words, just on their own as well as moving forwards. Now, what's really cool about this is that as soon as I make a difference to it, or in other words, I say that there's some amount of error, I can use my my parity check matrix, to determine which, I guess they call it syndromes, which syndrome it has, and then the syndromes correspond to specific errors. And if I know what those errors are, I can undo them and get my correct code out, which is the big point of all these past 2 topics, all right? So let's move forwards a bit. All right, so last 2 bits of information are, we have cyclic codes. Really, all it is you can cycle through different, I suppose, values. So if you have a code word of 4 zeros, then if I jump this one over to the other side, you've got another code word. That's the word. Sorry, I'm losing my mind. Same with if you have 1 here, that means that other code words are going to be given by 10000, 0111, 0011, 10, and so forth. So, good stuff.
Is something, is it not with the exam? Can they access it?
I'm not the most sure. It is in the course content.
When it says that it's not tested.
It might not be. But it's still something cool to understand.
Yeah.
So the idea of cyclic is you're able to feed in a certain number of bits, certain bit words, and then as soon as you, just like talking about the structure of the encoder, as soon as you turn off the input, it goes ahead and, I guess, almost flushes it and gives you a different output. That output, which is given over here, would be your code word. So it's a way of generating code words, unique code words for certain codes, given it behaves, really. If you wanted to make this a 4-bit encoder, then you could go ahead and add on another shift register and see how that goes. And then as soon as you hit it to B, you just run it until it hits all zeros, because it's going to flush to zeros in that sense. It's a very cool way of working this through. And yeah, it's a different matter for the cyclic decoder, because then you have to design that very strictly on your 7 and your 4, having 7 upper registers and your 3, I suppose, sorry, your K-1 decoding registers. Very cool stuff. Let's move forwards. A little bit of bonus info is interleaving and burst error correction. These are very, very cool. Why? Because errors can occur in bursts. So in other words, if I have some manner of noisy signal, let's say that the noise is given by this, and then continues, oh my gosh, every single bit that was in this region is going to likely have an error, right? So there's a burst of errors there. And we can imagine if we have a long code word that it's going to affect multiple bits, which is not good. Very not good. So, because it's not good, what we want to do is potentially distribute those errors across different bits and different code words. That makes it a lot more useful. So we use this little technique called interleaving by, we make a little matrix of like a packet of values where the rows are our messages, and then we actually just send them as columns, as we would see here. Because we're sending them as columns, mind you, this means we only get the full code words after all the columns are sent. It distributes your errors accordingly, as long as nothing extra goofy happens along the way. Decreases likelihood. It does mean that you have to reprocess it to turn it back into code words, to turn it back into your data, but this is one way that you can try and avoid errors. Okay?
So when you're sending it as columns, if you were to face an error, you would be able to detect the entire column of your code word being incorrect.
Well, the idea is that you break that column back into the rows, and then in that code word...
You can tell that the columns of the code words are incorrect.
Yes,
There's an
exactly.
error in every single code word.
Exactly.
and that one column.
So every code word only has like one error.
Yeah, which is then make it correct.
Exactly.
Maybe
So
it's like a visual.
it is a nice visualization for it. But it's very much the application of the previous concepts on top of this to correct it. Good stuff. So we have our final question, which we're going to race through. So question 5, this is the last question in the 2020 Term 1 final question 5. It's very similar to the 2024 paper, question 5, but they give us this condition. We want to go ahead and make a generator matrix given these parity check digits, and we have 3 data digits. So let's go ahead and do this. Typically in our generator matrices, we begin with a identity matrix. So this just identifies whatever our code word, what our data is, and then we're going to make these parity check digits. So we say that the first one, which we're going to call C4, is the sum of all 3 of these. So for us, this is going to be a 1 for all of these. Mind you, all these sums, for all this section, all your sums are in terms of base 2. So if you have 1 plus 1, it becomes 0. Okay, this is something very important to note because we're just working in binary and single digits. 1 plus 1 is 0. All right. So for the second one, we have D1 plus D2. And so these 2 are 1s, this is a 0. And then for the third one, we have D1 plus D3. This one's a 1, this is 0, this is a 1. Fantastic. All right, there we are. This is G. G equals this. This is part A. Done. Now I need to do part B. All right, so construct the code generated by this matrix to obtain code words for all 8 possible data words. How would we do this? Well, the idea is that we can generate code words by saying that C equals our data, I'm going to call it B, times G. So, mind you, this is a 3 by 6 matrix. And so if I multiply it by B, B has to be a something by 1 by 3. Wait, yeah, 1 by 3. So it's going to be rows, okay? So what I can actually do is I can say, okay, I'm going to let B, typically it's like a 1, 0, 1 kind of, okay, here's my value. I can set it to actually be the matrix. I can set B to be a matrix of using 3 rows, okay? Sorry, 3 columns, and then a number of rows for each code word. So I can set that up as such. Bam. You could gray code this. It doesn't really matter just in your calculation. But you'd have that. You would multiply by G, and you would end up with 8 different vectors. Okay. These vectors would be of length 6, and those would be your code words. Okay. So you get C as a big matrix equals this, B times Okay, so that's how you would do that. I reckon we have a bit of time to do that, so that should be very cool. Let's try and do this. So we go b times g is going to be equal to, so just remember, we take columns and we dot product with rows. So first we get a 0, and it's just the first identity running through all of these. So we get 4 zeros and then 4 ones. Next up, we get the second column, 0, 0, 1, 1, 0, 0, 1, 1. The third column, mind you, this is still just the identity, 0, 1, 0, 1, 0, 1, 0, 1. Going to make this bigger. And now we're going to start doing the additions. So here we have the fourth, which is going to be the sum of all 3 digits. And I can actually just see that, okay, my data is right here. So I'm just going to do my sums. So sum of all of these is going to give me 0, 1, 1, 0, 1, 0, 0, 1. Mind you, it's still mod 2. Now I need to do the sum of the first 2. So I get 0, 0, 1, 1, 1, 1, 0, 0. And then I do my sum of my first and third. If I look at my first and third, let's go ahead and do this. We get a 0, we get a 1, we get a 0. This is a little bit messy. 1, 1, 0, 0, 1. No, 0. This one's a 1.
Yeah.
Yes.
Cool.
There we go. All right, good stuff. And so our code words are given by the rows. This was the goofy row that was tripping me up.
For the first column, the 4 zeros and 4 ones, will it be like all zeros considering just multiplying by?
The first column, we have 4 zeros, 4 ones. You're asking why wouldn't it be all zeros? So the idea is we've multiplied by this column vector along these rows. So we're really just taking the first column. That's all good. All right. So yeah, we should always identify that these first 3 columns are just going to be whatever we chucked in from B. Okay? It's a very important understanding. And then this just happens when we perform our operation on that. So C1, C2, yada yada, C8. Fantastic. That's the code words. Now, error correcting capabilities. This is the main crux of this. We need to see, okay, here are all of our possible code words. What is the minimum Hamming distance between all of them? Mind you, calculating this would be a massive pain in the backside. So we can actually just try and identify if there are any error codes that we can determine. So the idea is we're going to make H, which is our, we can actually just like identify this from here. H is almost a manner of inverse, but it takes you to 0. So it goes ahead and it puts this chunk right here, puts it first. So you got all zeros, 1, 0, 1, 1, 1, 0. Actually, sorry, did I? No, sorry, that's the wrong matrix. That's B times G. It's maybe this part of the matrix, the parity part of the matrix. I was wondering why there was a 000. 000 is useless. Gives me no information. 111, 110, 101, and then you can do an identity here, fit to the size. Mind you, there are 3 columns, so I'm going to make identity square of 3. There we go. That is H, and we can use H to identify certain syndromes. Each of these columns is going to be a certain syndrome identified for a certain bit in the code word. Okay? All right. So if we have a code word that is modified by any one bit, it will output this code when it is incorrect, right? With that bit. that is the general gist of using your parity check stuff. To save you guys the hassle, I think the idea we want to apply here is we just identify, okay, what are the Hanning weights? Hanning weights 0, 3, 3, 4, 4, 3, 3, 4. So we know that the first one crosses off immediately because it is a minimum weight of 3 against the others. Something you can do from there is you could, there's a number of computationally intensive ways you could calculate this. I think the general shtick of it that you want to apply is that your Hanning weight of each of these is going to be at least 3, and they all work with error checking capability. It is very, very similar to one of the previous generators that we saw before. So to save you guys the time of checking what is the minimum Hanning distance, we'll say minimum is 3. All right, this is something that we can check somewhat manually. As for fast ways to check it, not really one in question. I believe for this question, what they wanted you to do was just identify really that, oh, wait a minute, this is a generator that we've seen before, because it is one of the most common ones, using all ones, then 2 of each. All right, that would do that. And then for the last parts of the question, which I guess we'll leave up to you guys, they want us to identify, okay, for these following code words, work them backwards, determine their syndromes, and therefore determine what they should actually be, right? Which is a very, very cool question in my opinion, right? Because I believe 2 of them or 3 of them have errors, and then you can use your H matrix to determine, okay, they have these syndromes, and therefore I need to fix these bits, which is pretty fantastic. All right, any questions? I think in the interest of time and the fact that I might have to, okay, let's do one. Let's do one. Okay, so beginning with 101100. So this is the received word. What we're going to do is we're going to say, okay, received word here, I need to multiply by H. Sorry, what do I need to multiply by? I know that Y, yes. So, code word, I multiply by H to get the syndrome. So let's go ahead and do that multiplication. So you go Y times H is going to give me, sum the first 4, I get a 1. Sum the first 2 and the 5th, I get a 1. And then sum the first, 3rd, and 6th. First, 3rd, and 6th, I get a 0. I believe. You can double check that. That seems correct. So what we're doing, we're multiplying this y, which is, I'm going to call it the row vector given by this, and then we're multiplying that by h, and so it gives us this value. Now mind you, this value of 110 is going to be, actually sorry, this might need to be a horizontal thing. It might, I'm pretty sure it's horizontal. My bad. That's what it gives. This is the syndrome for the second row. Okay, because it's the syndrome for the second row, that implies that your second bit is incorrect because it's a 1-bit error. And so it says that, oh, this bit right here is where the error is. Okay? And so because of that, we can say that the real word equals 111100, which gives the data equals 111 as such. All right? Good stuff. All right. That is the TELE crash course brought to a close. Final great thanks to Jackson for pulling this off. And as always, best of luck everyone with your exams. You guys got this. I believe TELE is on the 14th, so last day of our exam block. You guys got this. Go ahead and
Before you go, could you fill out the attendance form that we have?
Yes, I'll chuck that up right after I finish stream. So, let's
And you can also get
end
access
stream.
to all the slides that we made through that form as well, if you want to use it for revision.
Oh, well then. The slides.
Yeah, on the when you scan the
It's
QR
on
code.
the QR code.